Welcome to Cogni-Crafted Minds. Today, we're diving into the crucial world of unleashing the healing potential, abdominal trauma detection. Understanding abdominal injuries can make a huge difference in patient outcomes, and today, we'll explore how data can help us detect these injuries more effectively. Introduction. Welcome to an exciting journey into the future of healthcare. The RSNA Abdominal Trauma Detection AI Challenge is at the forefront of addressing a critical global issue: the prompt and accurate diagnosis of traumatic injuries in the abdomen using cutting-edge technology, computed tomography, or CT, scans. Traumatic injury is one of the leading causes of death worldwide. With the incredible detail that CT scans provide, they've become essential in evaluating patients with suspected abdominal injuries. However, interpreting these scans can be complex and time-consuming, especially when multiple injuries or subtle areas of active bleeding are involved. This is where artificial intelligence and machine learning step in. The challenge calls for innovative minds to develop advanced algorithms that can assist medical professionals in rapidly and precisely detecting these injuries and grading their severity. The ultimate goal? To improve trauma care and save lives across the globe. Let's dive into how this challenge is pushing the boundaries of what's possible in trauma care. Dataset overview. The dataset for the RSNA Abdominal Trauma Detection AI Challenge includes critical information about patients and their abdominal health. Each patient is identified by a unique patient ID. The dataset then provides a detailed look at the health status of various abdominal organs like the bowel, kidneys, liver, and spleen. For each organ, there are binary variables that indicate whether the organ is healthy or injured. For instance, bowel_healthy tells us if the bowel is in good condition, while bowel_injury indicates if there's an injury. Similar variables exist for the kidney, liver, spleen, and extravasation. Additionally, the dataset includes variables like kidney_low and kidney_high, which specify the severity of health status from low to high. Finally, there's an any_injury variable that sums up the total number of injuries detected in a patient, giving an overall view of the trauma severity. This dataset is the foundation on which participants will develop AI models to accurately detect severe abdominal injuries and any active internal bleeding. Now that we've explored the dataset, it's time to set up our environment by importing the necessary modules. Import modules. We'll begin by installing and importing the key Python libraries that will power our analysis and model building. First, we install the required packages using pip. This includes PyDicom for working with medical imaging data and Matplotlib for creating visualizations. Then, we import the libraries we'll be using throughout the project. Pandas is essential for data manipulation, while PyDicom helps us handle DICOM files, which are the standard format for medical images. We also import OS for interacting with the file system, and NumPy for numerical operations. For visualizations, we use both Matplotlib and Plotly, which allow us to create static and interactive plots, respectively. We'll also bring in k-means from scikit-learn for clustering and standard scalar for data preprocessing. Finally, we configure some settings to ensure our plots are clear and visually appealing. We set the figure size and use the 538 style for consistency. To avoid unnecessary distractions, we suppress warnings that might clutter the output. With these modules in place, we're ready to dive into the data and start our analysis. The next step is to load the dataset. We start by loading the dataset into a Pandas data frame, which is a powerful structure for managing and analyzing data. Using the read_CSV function, we'll read the data directly from the CSV file. Once loaded, we take a quick look at the first few rows of the dataset using the head function. This gives us an overview of the data we'll be working with. To make it visually appealing, we apply some styling, setting the background color to royal blue, text color to white, and border color to a subtle gray. This helps highlight the key data points, making it easier to spot any initial patterns or anomalies. Now that we've loaded the primary dataset, let's bring in some additional metadata to enrich our analysis. Load the metadata. We begin by loading another dataset, this time containing metadata, into a Pandas data frame. This metadata file provides extra details that can be crucial for a more comprehensive analysis. Just like before, we use the read_CSV function to load the data from the CSV file. This metadata might include information such as scan parameters, patient positioning, or other relevant details that complement our main dataset. To get an initial look at this data, we use the head function to display the first few rows. For clarity and emphasis, we style the output, setting the background color to orange, text color to white, and border color to a light gray. This makes the metadata stand out and easy to interpret. With the metadata now loaded and displayed, we're ready to move on to data preprocessing and analysis. With our dataset loaded, it's time to clean and prepare the data for analysis. This crucial step ensures that our data is accurate, consistent, and ready for modeling. Data preprocessing. We begin data preprocessing by checking for any missing values in the dataset. Missing data can lead to inaccurate results, so we need to identify and handle any gaps in the information. Using the isNull.sum function, we quickly sum up the missing values across all columns. If any missing values are detected, we'll decide how to address them, either by filling them in or removing them, depending on the situation. Next, we check the data types of our variables. It's important to ensure that binary data, which represents true or false values, is correctly formatted. In this case, we convert the binary columns to Boolean data types using the astype bool function. This helps to maintain consistency and avoid any potential errors during analysis. Finally, we address any data quality issues. In this example, we assume that there are no major data quality problems, but it's always good practice to be vigilant and check for anomalies or inconsistencies. With preprocessing complete, we print the updated data frame to verify that everything is in order. This step gives us a clean and well-structured dataset, ready for deeper analysis. After running our data preprocessing steps, let's review the results. Missing values. We checked for missing values across all columns, and the good news is that there are no missing values in the dataset. Each column, from patient_id to any_injury, is complete and ready for analysis. Preprocessed data frame. Next, we take a look at the preprocessed data frame. Here, we can see a few rows of our cleaned data. The binary variables, such as bowel_healthy, bowel_injury, kidney_healthy, and more, have been successfully converted to Boolean values, with true indicating a positive condition and false indicating the absence of that condition. For instance, in the first row, we see that the patient has a healthy bowel, but there's an injury detected in the extravasation, and their spleen is not healthy. Additionally, the any_injury column shows that this patient has one injury in total. The data frame now consists of 3,147 rows and 15 columns, giving us a well-structured and clean dataset that's ready for further analysis and model building. With our data preprocessed and ready, it's time to dive into some descriptive statistics to get a better understanding of the dataset's overall structure. Descriptive statistics. We start by generating summary statistics for the key variables in our dataset. These statistics give us insights into the central tendencies, variability, and distribution of our data. Using the describe function in Pandas, we compute essential metrics such as the mean, standard deviation, minimum, and maximum values for each variable. This provides a snapshot of the data's overall behavior. To make the output more visually engaging and easier to interpret, we apply a cool-warm color gradient. This color scheme helps to highlight different ranges of values, with cooler tones representing lower values and warmer tones indicating higher ones. We also ensure the text is centered and bordered for clarity and professionalism. Finally, we display the styled data to examine these summary statistics. This step allows us to spot any potential outliers, trends, or patterns in the data, setting the stage for more in-depth analysis. Next, let's dive into the categorical variables to understand their distribution and significance within the dataset. Analyzing categorical variables. We start by focusing on our key categorical variables, such as the health status and injury presence across different organs like the bowel, kidney, liver, spleen, and extravasation. These variables are critical for understanding the condition of the abdominal organs and identifying any patterns in injuries. First, we generate counts for each category. This tells us how many instances fall under each condition, whether it's healthy or injured. For example, how many patients have a healthy bowel versus those who have sustained an injury. In this section, we'll be generating counts and percentages for the categorical variables in our dataset. This process allows us to better understand the distribution of different health and injury statuses among our patients. We start by defining the list of categorical columns that we want to analyze. These columns represent different health and injury conditions for various organs. Next, we calculate the counts for each category within these columns using the value_counts function from pandas. This function counts the occurrences of each unique value within a column. After obtaining the counts, we calculate the percentages by dividing the counts by the total number of rows in the dataset and multiplying by 100. This gives us the percentage representation of each category in the dataset. Finally, we display the counts and percentages. The counts show how many patients fall into each category, while the percentages provide a relative view of these counts in the context of the entire dataset. By generating these counts and percentages, we gain valuable insights into the prevalence of various health and injury conditions among our patients. This information is crucial for understanding the overall health profile of the patient population and for identifying any significant trends or patterns. Let's walk through the summary statistics for our dataset, focusing on the counts and percentages of categorical variables related to different health and injury statuses. Counts of categorical variables. Starting with the counts, we can see how many patients fall into each health or injury category. Bowel health. Out of the total patients, 3,083 are classified as having a healthy bowel, while 64 have bowel injuries. Conversely, 3,083 patients are classified as having bowel injuries. Extravasation status. For extravasation, 2,947 patients are marked as healthy, while 200 have injuries. This shows that extravasation injuries are relatively rare compared to the healthy status. Kidney health. In the case of kidneys, 2,965 patients are considered healthy, with a smaller group of 182 showing low kidney function, and an even smaller group of 67 patients categorized as having high kidney function. Liver and spleen conditions. The liver and spleen conditions show similar trends, where the majority of patients are classified as healthy, with fewer patients having low or high conditions. Any injury. When considering any injury, 2,292 patients have no injuries, while 855 patients have at least one injury. Percentages of categorical variables. Next, let's look at the percentage representation of these categories. Bowel health. 97.97% of the patients have a healthy bowel, while only 2.03% have bowel injuries. Extravasation status. Similarly, 93.64% are healthy, with only 6.36% showing injuries. Kidney health. The majority of patients, 94.22%, have healthy kidneys, 5.78% have low kidney function, and 2.13% have high kidney function. Liver and spleen conditions. About 89.80% of patients have healthy liver conditions, while 10.20% do not. For the spleen, 88.75% are healthy, with 11.25% showing conditions of concern. Any injury. Finally, when we look at any injury status, about 72.83% of the patients have no injuries, while 27.17% have some form of injury. Summary. These counts and percentages provide a clear picture of the health status distribution among the patients in our dataset. We can see that certain conditions, such as bowel and kidney health, are predominantly healthy, while other conditions like any injury are more evenly distributed between healthy and injured statuses. This information is vital for understanding the overall health landscape and identifying key areas that may require further investigation or intervention. Let's delve into exploratory data analysis, EDA. EDA is a crucial step in understanding the underlying patterns and relationships within our data. In this section, we'll explore various techniques to uncover insights and trends. First, we'll visualize the distribution of different variables using appropriate plots. Bar plots will help us understand the frequency of categorical variables, such as the number of cases with healthy versus injured organs. Pie charts are excellent for illustrating the proportion of each category, giving us a quick overview of how different conditions compare. Histograms will allow us to examine the distribution of continuous variables, such as age or blood pressure, and see how these values are spread across our dataset. Next, we'll analyze the relationships between variables. For example, we'll look at the correlation between organ health and injury status. This analysis will help us identify any significant connections or patterns, such as whether a particular organ's health is linked to a higher likelihood of injury. We'll also explore any noticeable patterns or trends in the data. Are there specific variables that consistently show a strong relationship? Do certain patterns emerge when we look at different subgroups or conditions? This exploration will provide us with valuable insights into how various factors interact with each other. Finally, we'll visualize a sample image to illustrate our findings. This could be a representative plot or a snapshot of a significant trend we've discovered, providing a clear visual representation of the data insights we've gained. Through these EDA techniques, we aim to build a comprehensive understanding of our data, setting the stage for deeper analysis and more informed decision-making. In this step, we focus on visualizing the distribution of health and injury statuses across different organs using a bar plot. First, we define the list of organ columns, which includes bowel, extravasation, kidney, liver, and spleen. These are the organs we'll analyze. We then create a new data frame, organ_counts, to store the counts of healthy and injury statuses for each organ. The data frame is initialized with a single column, organ, containing the names of the organs. Next, we loop through each organ in our list. For each organ, we dynamically construct the column names for healthy and injury statuses by appending _healthy and _injury to the organ name. We then check if these columns exist in our original data frame, DF. If the columns are present, we calculate the sum of healthy and injury statuses for that organ and store these counts in our organ_counts data frame. If the columns are missing, we print a warning message and set the counts to 0 to handle the missing data gracefully. After collecting the data, we use the melt function to reshape our data frame. This transformation turns our wide data frame into a long format, creating a status column that combines both healthy and injury statuses, and a count column for their respective values. Finally, we create a bar plot using Plotly Express. The plot displays the distribution of organ health and injury statuses, and group the bars by organ. The plot is titled, Distribution of Organ Health and Injury Status, and includes labels for better clarity. By visualizing this data, we can easily compare the health and injury statuses of different organs and identify any significant patterns or trends. Distribution of organ health and injury status. Now, let's dive deeper into the distribution of health and injury statuses for these organs. The bowel shows 3,083 healthy cases and 64 injuries. When it comes to extravasation, we see 2,947 healthy cases and 200 injuries. For the kidneys, there are 3,083 healthy cases and 64 injuries, which mirrors the bowel statistics. In the liver, we observe 2,947 healthy cases with 200 injuries, similar to extravasation. Finally, in the spleen, we also see 2,947 healthy cases and 200 injuries. The distribution reveals that while most organs remain healthy, there are still significant cases of injuries that should not be overlooked. This segment visualizes the distribution of health and injury statuses across the bowel, kidney, liver, and spleen. The plot emphasizes the predominance of healthy cases, but it also highlights the presence of injuries, especially related to extravasation, which is consistent across multiple organs. This insight is valuable for understanding the overall health and identifying areas where injuries are prevalent. Now, we'll explore the correlation between organ health and injury statuses using a heat map. We start by defining the list of organ columns, which includes bowel, extravasation, kidney, liver, and spleen. We then generate a list of corresponding injury columns by appending _injury to each organ name. Next, we check if all necessary columns, including both health and injury statuses, are present in the data frame. We create a set of these required columns and compare it with the columns actually available in DF. If any columns are missing, we print a warning message to notify us of the missing data. To handle this, we add the missing columns to the data frame and initialize them with zeros. After ensuring that all required columns are present, we create a data frame, correlation_DF, that includes only the organ and injury columns. We then compute the correlation matrix using the CORE method. This matrix shows how strongly the health and injury statuses of different organs are related to each other. Finally, we visualize the correlation matrix using a heat map with Plotly Express. The heat map displays the correlation coefficients between each pair of variables, with color intensity representing the strength of the correlation. The axes are labeled with organ names, and the color bar indicates the correlation values. The title of the heat map is Correlation between Organ Health and Injury Status. This visualization helps us understand the relationships between different organ conditions and their injury statuses, highlighting any significant correlations that may exist. Let's explore the correlation between organ health and injury status, as depicted in this plot. Correlation values help us understand the strength of the relationship between the health of different organs and the presence of injuries. Yellow color correlation. For the bowel injury, we see a perfect correlation of 1 with itself, which is expected because it's the same measure repeated. Similarly, for extravasation injury, there's also a perfect correlation of 1 with itself, highlighted in yellow. Dark blue color correlation. When we compare bowel injury with extravasation injury, the correlation drops significantly to 0.12857725. This value indicates a weak positive correlation, suggesting that while there may be some relationship between injuries in these two organs, it's not very strong. These color-coded correlations provide a visual understanding of how closely related the health and injury status of different organs are. The yellow color highlights perfect correlations, while the dark blue color shows weaker correlations. This information is crucial for identifying which organs' health statuses are more likely to influence one another when it comes to injuries. As we move forward, let's focus on visualizing a sample image from our dataset. This step will help us understand the kind of data we are working with and ensure that our images are correctly processed for further analysis. To begin, we need to import the necessary library, PyDicom, which is used for handling DICOM files. We'll define a function, standardize_pixel_array, to process the DICOM images. This function takes a DICOM dataset as input and corrects the pixel array if the pixel representation is set to 1. The correction involves adjusting the pixel values based on the bit depth of the image, ensuring that the pixel data is accurately represented. We then load the DICOM tags from a Parquet file using pandas. This file contains metadata for the images, and we will access it to find the path to a sample image. For our demonstration, we select the image at index 49954 from the dataset. With the image path identified, we use PyDicom to read the DICOM file. The file is located in a specified directory, and we read it into a DICOM dataset object. Finally, we display the first few rows of the DICOM tags to give us an overview of the metadata associated with the images. Visualizing this sample image allows us to verify that our image loading and processing pipeline is functioning correctly. It also gives us an idea of the quality and characteristics of the images in our dataset. We'll now focus on visualizing a specific sample DICOM image using the plot_decom_image function. In the provided code, we first specify the path to the sample DICOM image using the variable sample_image_path. This path points to a DICOM file located in our dataset directory. We then call the plot_decom_image function with this path as the argument. The function is responsible for reading and displaying the DICOM image. It uses PyDicom DCM read to load the image from the file path. The pixel data from the DICOM file is then rendered using matplotlibs show function. We apply the bone color map to enhance contrast and make the details more visible. Additionally, the axis labels are turned off using PLT axis off to provide a cleaner view of the image. Finally, PLT show is called to display the image in a plot window. This visualization allows us to examine the specific DICOM image, providing insights into its content and quality. We'll now walk through the process of loading and visualizing DICOM images from a directory using our defined functions. First, we have the load_decom_images function. This function is designed to load all DICOM images from a specified directory. It begins by creating an empty list called decom_images to store the loaded images. The function then iterates over all files in the provided directory. For each file that ends with the .dcm extension, it constructs the full path to the file and reads the DICOM image using PyDicom DCM read. Each loaded image is appended to the decom_images list. After processing all files, the function returns the list of DICOM images. Next, the rescale_pixel_array function is used to adjust the pixel values of the DICOM images. It takes a pixel array, a window level, and a window width as inputs. The function calculates the minimum and maximum pixel values based on the window level and width, then clips the pixel values to this range. The pixel values are normalized to a range between 0 and 1 to facilitate visualization. The visualize_decom_images function creates a grid of subplots to display the DICOM images. We set up a grid with a specified number of rows and columns. For each subplot, if there is a corresponding DICOM image, we extract the pixel data, rescale it using rescale_pixel_array, and display it with the bone color map. The axis labels are turned off for a cleaner view, and each subplot is titled with its slice number. If there are fewer images than the total number of subplots, the remaining subplots are hidden. Additionally, a color bar is added to the side of the grid to show the pixel intensity values, which helps in interpreting the images. Finally, in the if_name_equals_main__ block, we specify the directory path where the DICOM images are located. We call load_decom_images to read the images from this directory and then call visualize_decom_images to display them in a 3x3 grid with the specified window level and width. Multiplanar reconstruction, MPR. Next, we will explore multiplanar reconstruction, or MPR, a technique used to display slices of medical images in different planes simultaneously. This method allows us to view the same data from multiple perspectives, axial, sagittal, and coronal, providing a comprehensive understanding of the anatomy. To implement MPR, we can use various libraries, and for our example, we'll use Matplotlib, a powerful library for creating static, animated, and interactive visualizations in Python. In our approach, we'll visualize the DICOM slices in 3 orthogonal planes. Axial plane, the horizontal slice view. Sagittal plane, the vertical slice view from the side. Coronal plane, the vertical slice view from the front. We start by importing Matplotlib, PyPlot to handle plotting. The process involves setting up a grid of subplots to display the 3 planes simultaneously. Each subplot will show the image data for one of the planes. Here's a high-level overview of how we'll achieve this. Load the DICOM image data. Extract slices from the DICOM image dataset for each of the 3 planes. Set up subplots. Create a figure with 3 subplots, each corresponding to one of the planes. Plot the slices. Use IMShow to render the images for the axial, sagittal, and coronal planes in their respective subplots. Customize the display. Add titles and adjust the layout for clarity. This visualization helps in understanding the spatial relationships between different slices and aids in accurate diagnosis and analysis. In this section, we'll use Matplotlib to visualize multiplanar reconstruction, MPR, of DICOM images. MPR involves displaying slices in different anatomical planes, axial, sagittal, and coronal. Our goal is to create a side-by-side view of these planes to better understand the spatial relationships within the data. Let's break down the code for the display_MPR function, importing the library. We begin by importing Matplotlib, PyPlot as PLT, which provides us with the tools to create our visualizations. Defining the display_MPR function. The display_MPR function takes a list of DICOM images as input and sets up a figure with 3 subplots arranged in a single row. The fig size parameter determines the size of the entire figure, displaying the axial slice. In the first subplot, index 0, we display the axial slice by rendering the pixel array of the first DICOM image using a grayscale color map. The title, axial, is added for clarity, displaying the sagittal slice. For the second subplot, index 1, we show the sagittal slice. Here, we transpose the pixel array of the second DICOM image to adjust the orientation and use the origin equals lower parameter to correctly orient the image. The title, sagittal, is added, displaying the coronal slice. Similarly, in the third subplot, index 2, we display the coronal slice by transposing the pixel array of the third DICOM image. The title, coronal, is included. Final touches. We turn off the axis labels for all subplots to provide a cleaner view of the images. Displaying the plot. Finally, PLT. Show is called to render the figure with the 3 subplots. This function assumes you have 3 DICOM images representing the axial, sagittal, and coronal planes. By calling display_MPR, DICOM_images, you will get a clear, side-by-side view of these planes to aid in your analysis. Next, we dive into the analysis of organ health. In this section, we'll compare the prevalence of healthy, low, and high health conditions across various organs, namely, the bowel, extravasation, kidney, liver, and spleen. Our goal is to identify which organs have the highest and lowest health status based on the data provided. We start by loading our dataset, which contains the health status of different organs. Here's the code to analyze and visualize this information. Loading the dataset. We begin by loading our dataset into a data frame using pandas. This dataset includes columns that indicate the health status of various organs. Organ columns. We specify the list of organs we're interested in analyzing. Counting health conditions. For each organ, we calculate the total count of healthy, low, and high health conditions. If the corresponding columns for low and high health are missing, we handle this by setting the counts to 0. Creating the plot. We use Plotly to create a stacked bar chart that visualizes the count of each health condition for every organ. The bar mode equals stack parameter allows us to stack the bars for a clear comparison. Updating the layout. We customize the chart's layout, including titles for the axes and the legend to help interpret the data. Displaying the plot. Finally, we render the plot to visualize the health status of the organs. This analysis helps us understand the distribution of health conditions across different organs and identify which organs are most and least affected. Comparison of organ health prevalence. Let's explore the health status of various organs and see how they compare. We're going to look at the number of healthy, low health, and high health conditions for the bowel, kidney, liver, and spleen. For the bowel, the total number of healthy cases is 3,038. When we look at extravasation, a condition related to fluid leakage, there are 2,947 healthy cases. Moving on to the kidneys, there are 2,965 healthy cases, but we also see 115 cases with low health and 67 cases with high health. For the liver, we observe 2,826 healthy cases, 259 with low health, and 62 with high health. Lastly, the spleen shows 2,793 healthy cases, with 199 in low health and 155 in high health. This comparison helps us understand which organs tend to have more health issues and where medical attention might be needed most. We compare the prevalence of health conditions across different organs. The plot clearly shows that most organs have a majority of healthy cases, but the kidneys, liver, and spleen also exhibit a notable number of low and high health cases. The data can guide us in identifying organs that may require more medical focus. Now, let's dive into the analysis of injuries across different organs. We'll start by examining the occurrence of injuries in various organs. In this part of the code, we've defined a list of columns that correspond to injuries in different organs. By summing the values in these columns, we get the total count of injuries for each organ. Next, let's visualize these counts using a bar plot. Here, we use Plotly to create a bar chart that displays the total number of injuries for each organ. This visualization helps us quickly grasp which organs have the highest counts of injuries. To understand the overall prevalence of injuries in our dataset, we'll look at the total count of injuries recorded. This line calculates the total number of instances where any injury is recorded, providing an overall measure of injury prevalence across the dataset. Finally, we investigate if there's any relationship between injuries in different organs. Occurrence of injuries in different organs. Let's examine the occurrence of injuries across different organs, as shown in this bar plot. This visualization highlights how often each organ is injured within our dataset. Bowel injury. The plot shows that the bowel has experienced 64 injuries, making it one of the most frequently injured organs. Extravasation injury. Extravasation injuries are slightly less common, with 21 occurrences recorded in the dataset. Kidney injury. The kidney shows a moderate level of injury, with 45 occurrences noted, indicating a significant risk. Liver injury. The liver also has a high number of injuries, with 37 injuries documented, making it a key organ of concern. Spleen injury. Lastly, the spleen has 41 injuries, placing it in the middle range compared to the other organs. These values give us a clear understanding of which organs are more frequently injured. Such insights are crucial for healthcare professionals, helping them to focus their attention on the organs most at risk and to develop targeted preventive measures. Correlation between injuries in different organs. Let's explore the correlation between injuries in different organs, using a correlation matrix that helps us understand how injuries in one organ might relate to injuries in another. Starting with bowel injuries, we see that there's a correlation of approximately 0.236 with any type of injury, indicating a mild relationship. This suggests that when bowel injuries are present, there might be a slightly increased chance of other injuries as well. When we look at the correlation between bowel injuries and extravasation injuries, the correlation is weaker, around 0.129. This indicates that these two types of injuries don't strongly influence each other, but there is still a slight connection. Interestingly, the correlation between bowel injuries with themselves is 1, which makes sense because an organ is perfectly correlated with itself. Now, let's focus on extravasation injuries. We observe a stronger correlation of approximately 0.427 with any injury, suggesting that extravasation injuries are more likely to occur alongside other injuries compared to bowel injuries. Similarly, the correlation between extravasation injuries with themselves is also 1, indicating a perfect correlation. Finally, when we look at the correlation between any type of injury with other injury types, we see a stronger correlation with extravasation injuries at around 0.427, and a moderate correlation with bowel injuries at around 0.256. These correlations help us identify patterns in how different injuries might co-occur, providing valuable insights for understanding injury mechanisms and guiding clinical assessments. Any injury versus organ health. In this section, we'll explore the relationship between the presence of any injury and the health status of each organ. Specifically, we'll calculate and visualize the percentage of patients with any injury across different organ health categories. Let's start by defining a function to calculate the percentage of patients with any injury for each health category of an organ. Here, calculate _injury %% takes two arguments: the column representing the health status of the organ and the column indicating the presence of any injury. It groups the data by the health status and computes the mean percentage of patients with any injury, which is then multiplied by 100 to convert it into a percentage. Next, we apply this function to each organ to get the injury percentages. We define organ_columns with the names of the organs and use a dictionary comprehension to calculate the injury percentages for each organ. The resulting dictionary contains the percentage of patients with any injury, grouped by the health status of each organ. Finally, we visualize this data using a bar plot. In the plot, each bar represents the percentage of patients with any injury, segmented by the health status of the organ. Percentage of patients with any injury for each organ health category. Let's take a closer look at the percentage of patients with any injury across different organ health categories. This bar plot breaks down the data by showing how likely patients are to have injuries based on whether their organs are classified as healthy, low health, or high health. Bowel. For the bowel, we see a striking pattern. 0% of patients with healthy bowels have any injury, while 100% of patients with low or high bowel health have sustained injuries. Extravasation. Similarly, in the case of extravasation, 100% of patients with healthy status have injuries, whereas 0% of patients with low or high health status have any injury. Kidney. The kidneys follow the same trend as extravasation, with 100% of patients in the healthy category showing injuries, and 0% in the low or high health categories having injuries. Liver. The liver exhibits a pattern similar to the bowel, with 0% of patients in the healthy category having any injury, but 100% of those with low or high liver health experiencing injuries. Spleen. Finally, for the spleen, 100% of patients with healthy status have injuries, and 0% of patients in the low or high health categories have injuries. For the bowel, we observe a percentage of 25.65683% for patients with injuries. In the case of extravasation, the percentage stands at 22.22599%. The kidney shows a percentage of 22.69815% for patients with injuries. Moving on to the liver, the percentage is 18.89597%. Lastly, the spleen has a percentage of 17.9377%. These specific values highlight the variability in injury occurrence across different organs, providing a more detailed understanding of how health status impacts injury likelihood.
Patient profiles. In this segment, we'll identify patient profiles based on their organ health and injury status. By grouping patients with similar organ health and injury patterns, we aim to uncover any patterns or common characteristics among those with injuries. We'll start by preparing the data for clustering. This involves selecting relevant columns related to organ health and injury status. Here, we gather columns related to the health status of organs and the presence of injuries into the patient_data data frame. Next, we standardize the data to ensure that all features contribute equally to the clustering process. We use standard scaler to scale the features so that each has a mean of 0 and a standard deviation of 1. Then, we perform k-means clustering to group patients into clusters based on their organ health and injury status. Here, we apply k-means clustering with two clusters, assuming one group represents healthier patients and the other group represents those with more injuries. The resulting cluster labels are added to the data frame. We then count the number of patients in each cluster. Finally, we visualize the patient profiles using a bar plot.
Let's take a look at the patient profiles based on their organ health and injury status. This bar plot shows the number of patients categorized into two distinct clusters, healthy and injured. In our dataset, we identified Cluster 0. This represents the healthy patients with no injuries. Interestingly, there is only one patient in this cluster, reflecting a small subset of our data. Cluster 1. This cluster includes injured patients, each with at least one injury in their organs. Here, we find a total of 4 patients. Overall, the dataset contains 2,947 healthy individuals and 200 injured ones. However, due to the small sample size used for clustering, only 2 clusters emerge, one for the healthy patient and one for the injured patients. In larger datasets, more complex and meaningful patient profiles might emerge, allowing us to dive deeper into the common characteristics among patients, especially those who are injured. This kind of analysis is crucial for identifying patterns and improving patient care strategies. Build model and prediction. In this section, we will build a machine learning model to classify data and evaluate its performance. We'll use a synthetic dataset to demonstrate the process, and apply various classifiers to make predictions. Let's dive in. First, we create a synthetic binary classification dataset using. In this step, we generate a dataset with 500 samples, 2 features, and 2 classes. The parameters n_informative, n_redundant, and n_repeated control the number of informative, redundant, and repeated features, respectively. Next, we split the dataset into training and testing sets. Here, we use 80% of the data for training and 20% for testing to evaluate our model's performance. We then train a logistic regression model on the training data. The logistic regression model is trained to distinguish between the 2 classes based on the features. After training, we make predictions on the test set. We then calculate and display the model's accuracy and confusion matrix. The accuracy score gives us the proportion of correctly classified samples, while the confusion matrix provides a detailed breakdown of the true positives, true negatives, false positives, and false negatives. In summary, this process allows us to evaluate how well our model performs on unseen data and assess its classification accuracy. Random forest confusion matrix. Now, let's move on to the confusion matrix generated from a random forest model. Here's what we see. Predicted negative, true positive, the value is 1. This means the model predicted a negative outcome, but the actual result was positive, and this happened once. Predicted positive, true negative, the value here is 3. This shows the model predicted a positive outcome when the actual result was negative, and it occurred 3 times. Predicted negative, true negative, we have a value of 48. This means the model correctly predicted negative outcomes 48 times. Predicted positive, true positive. Lastly, the value is 48. This indicates the model correctly predicted positive outcomes 48 times. In summary, this confusion matrix suggests that the random forest model is generally performing well, especially in predicting true negatives and positives, but there are still a few false predictions to be aware of. Explanation. The random forest confusion matrix shows 1 false negative. The model incorrectly predicted a negative outcome when it should have predicted positive. 3 false positives. The model incorrectly predicted a positive outcome when it should have predicted negative. 48 true negatives. The model correctly predicted negative outcomes. 48 true positives. The model correctly predicted positive outcomes. This matrix demonstrates that the random forest model has a strong ability to correctly predict both positive and negative outcomes. SVM confusion matrix. Let's take a look at the confusion matrix generated from a support vector machine, or SVM model. A confusion matrix is a table that shows how well our model is doing by comparing the predicted results with the actual outcomes. Here are the details from the matrix. Predicted negative, true positive. The value is 1. This means the model predicted a negative outcome when the actual result was positive, and this occurred once. Predicted positive, true negative. The value here is 8. This indicates the model predicted a positive outcome, but the actual result was negative, happening 8 times. Predicted negative, true negative. We have a value of 43. This means the model correctly predicted negative outcomes 43 times. Predicted positive, true positive. Finally, the value is 48. This tells us that the model correctly predicted positive outcomes 48 times. Overall, this confusion matrix gives us insight into how the SVM model is performing. While it's doing well in predicting true positives and negatives, there are still some instances of false predictions, especially false positives, that we need to address. Explanation. The SVM confusion matrix highlights the following. 1 false negative. The model incorrectly predicted a negative outcome when it should have predicted positive. 8 false positives. The model incorrectly predicted a positive outcome when it should have predicted negative. 43 true negatives. The model correctly predicted negative outcomes. 48 true positives. The model correctly predicted positive outcomes. This matrix helps us understand where the SVM model excels and where it struggles, particularly with false positives. Welcome to this quick breakdown of a confusion matrix generated from a gradient boosting model. In this matrix, we are analyzing the performance of our model by comparing predicted outcomes with the actual results. Let's start with the basics. The confusion matrix is a table that describes the performance of a classification model. It's composed of 4 key values: true positives, true negatives, false positives, and false negatives. Now, let's go through the matrix values. Predicted negative, true positive. We have a value of 1. This means the model predicted a negative outcome, but the actual outcome was positive, and this happened 1 time. Predicted positive, true negative. We see a value of 4. This indicates the model predicted a positive outcome, but the actual result was negative, and this occurred 4 times. Predicted negative, true negative. Here, the value is 47. This tells us that the model correctly predicted negative outcomes, matching the actual results, 47 times. Predicted positive, true positive. Finally, we have a value of 48. This shows that the model correctly predicted positive outcomes, which also matched the actual results, in 48 instances. In summary, this confusion matrix gives us a snapshot of how well our gradient boosting model is performing. High values in the true positive and true negative categories suggest that the model is accurately classifying the outcomes most of the time. However, we still have some instances where the model makes incorrect predictions, highlighted by the non-zero values in the false positive and false negative categories. Understanding these results helps us fine-tune our model for better accuracy in future predictions. Evaluation metrics. In this section, we'll evaluate our model's performance using the log loss metric. Log loss, also known as logistic loss or cross-entropy loss, measures the performance of a classification model where the prediction is a probability value between 0 and 1. It essentially quantifies the uncertainty of our predictions by penalizing false classifications more heavily based on their probability. Let's dive into how we calculate log loss for our dataset. Here, we first extract the predicted probabilities for the bowel_injury class, which our model has generated, and the actual true labels for the any_injury class from our data frame. These values will be used to compute the log loss. We then compute the log loss using the log_loss function from sklearn metrics. This function takes the actual labels and the predicted probabilities as inputs and calculates the log loss for our dataset. Note that log_loss expects predicted probabilities and actual labels as its arguments, so ensure that your data is in the correct format. Finally, we add the calculated log loss values to our data frame for each patient. This addition allows us to see the log loss metric alongside our existing data and evaluate the model's performance across different instances. The log loss metric helps us understand how well our model's predicted probabilities align with the actual outcomes. A lower log loss indicates better model performance. In this section, we will visualize the log loss values for each patient using both a bar plot and a scatter plot. Let's break down the code and what it represents. First, we sort the data frame by the log_loss column in ascending order. This step ensures that the patients with the lowest log loss values are at the top of the list. Next, we create a plotly figure to hold our plots. We begin by adding a bar plot to the figure. This bar plot displays the log loss values for each patient, with the patient_id on the x-axis and the log_loss values on the y-axis. Here, we specify that the bar color should be blue and display the log loss values rounded to 4 decimal places as hover text. The text is positioned outside the bars for clarity. We then add a scatter plot to the figure. This scatter plot places markers at each patient_id and log_loss value. The markers are red and have a size of 10 to make them prominent. Finally, we update the layout of the figure to include titles for the x-axis and y-axis, and to ensure the legend is visible. By displaying both the bar plot and scatter plot together, we gain a clear view of how log loss values are distributed across patients. The bar plot shows the exact values, while the scatter plot provides a visual representation of the data distribution.
You can find all the code from my notebook using the link below.
Thank you for watching. If you found this video helpful, please subscribe, please like, for more content on machine learning and data science. See you in the next video.